Okay, let's walk through another sample problem. This is 13-53 from the textbook. This problem is several parts. There's really four different parts to it. I chose this problem because it shows more or less every way these integrated rate equations can be used, solving for different variables using a similar equation. So I figured I could just work through it and it would be a good illustration for you. It's dealing with the decomposition of this compound. It's a first order process with a rate constant equal to this, so they give you the rate constant at a certain temperature. We're also told it's a first order process, which tells us which of the rate laws to use, which are the integrated rate laws. We're then asked four different things. First off, what is the half-life? Secondly, how long will it take for the concentration of the substance to decrease to 25% of the initial value? If the initial concentration is 1 molar, how long is it going to take to decrease to 0.78 molar? You can see that decimal place right there. And lastly, if the initial concentration is 0.15 molar, what is the concentration after 200 seconds? I think you're also asked after 500 seconds, and I basically cut that off because it's essentially the same calculation just with a different time. Okay, so I've broken this down already on the bottom. I'm starting to answer some of these because I didn't think I could get through it in the 15-minute time limit of a YouTube video without sort of prepping in advance. But I'll walk you through the calculation and what the thought process is for each of these, okay? So for part A, you're just asked what is the half-life. Okay, now for each of the integrated rate laws, depending on the order, 0, first, or second order, you can basically derive different half-life equations. These are given in that end of the chapter section where it talks about the key objectives for the chapter. It gives some key equations and vocabulary. There's a table there with all these equations, not only the integrated rate laws, but also the half-life equations. So this half-life equation, T1/2, is equal to 0.693 divided by K. That basically applies to a first-order reaction. Now I'm told it's a first order in the problem, so I can basically just plug and chug, and I'm done. So for any first order decay, 0.693 divided by the rate constant K gives you the half-life. So for this particular circumstance, I do 0.693 divided by my K that I've stated in the problem is 1.42 times 10 to the minus 4 per second. I get a half-life of 4,880 seconds. Simple as that, just plugging and chugging basically. But you need to know the equation and know that you have different equations for different processes, different orders of reactions. This is the one for the first order and only for first order. The next question asks you, how long is it going to take for the concentration of the substance to decay to 25% of what was originally present. So 75% of the molecules have decayed and 25% is left. How long is that going to take? Okay. Well, you might be confused by this problem at first because you're not given any initial concentrations in the problem. You're certainly not given any concentration in question B. So you could think that, I just need to plug in numbers into the integrated rate equation, solve for T, how long it's going to take. And that thought process is not a bad one, except you don't have an initial concentration to use. You're just speaking in percentages, okay? Well, when I read this, I more or less immediately recognized that to have 25% of the original material left is essentially equal to 2 half-lives, right? Because the definition of a half-life is how long it's going to take for half of the stuff to decay away. So this is 1 half-life, and after that, you're left with 50% of the original. If you wait 2 half-lives, you're left with 25%, okay? So basically, this is a pretty easy problem as well. All you need to do is multiply the half-life times 2. So I got is 9760. We're done, okay? Easy as that. So, but you had to recognize it's 2 half-lives. It's a little bit tricky, okay? It'd be even trickier if I said 12.5% of original left, and then you could realize it's 3 half-lives, but you get the idea. All right, so part C. If the initial concentration of the substance is 1 molar, how long is it going to take to decrease to 0.78 molar? So this is our final concentration. This is our initial concentration. So this is kind of a prototypical integrated rate law type of question. You're given a couple of measurements or values. You plug them in and use the integrated rate law to solve for T, the time required. So for a first order process, this is the integrated rate law, the natural log of A, the concentration of the substance at time T, is equal to minus kT plus natural log of A0, where this is the initial concentration. So it's just a plug and chug from here, okay? The initial concentration we're told is 1 molar here. I plug in the 1, take the natural log of that and get 0. Moving on, I have negative kT here. Well, K is just my rate constant. I'm given that in the problem. It's 1.42 times 10 to the minus 4th per second. And I multiply that by T, which is the time. Now, that's the time required to reach the final concentration. So that's going to be our unknown variable here. Over on the left-hand side of the equation, I have natural log of A at time t. This is the concentration at some time t after the beginning of the sampling period or the start of the reaction. So here I'm going to take the natural log of 0.78 because that was specified as the second concentration. Right? How long is it going to take to decrease from the 1 molar to the 0.78 molar, or the less concentrated solution? So I have natural log of that because that's my concentration at time t. Take the natural log, I get this value. If I multiply this out, I get negative 1.42 times 10 to the minus 4t plus 0 is equal to this. I can quickly get rid of the 0. That doesn't do anything over here. Do the division to solve for t, which is my unknown variable, and I get t is equal to 1.75 times 10 to the 3rd seconds. So that solves A through C. Let me do some erasing here, and then we'll move on and talk about part D. So what does part D ask us about? It says if the initial concentration's 0.15 moles per liter, what concentration is left after 200 seconds after letting the reaction proceed, okay? Well, again, we're going to go back to the form of our integrated rate law. It says that the natural log of the concentration of the reacting substance at some t is equal to minus kT times the natural log of the concentration of that substance at time equals 0. So we basically have to plug in some numbers and see what we got and what we can solve for, okay? It's easy as that. So what do we know? Well, the initial concentration was said to be 0.15 moles per liter. So it sounds like to me I need to plug in 0.15 out here for my A0 and take the natural log of that ultimately, okay? Now, I also know my rate constant. I was told that in the problem. It was 1.42 times 10 to the minus 4 per second. In the form of my integrated rate law, it tells me I need to multiply that rate constant times t, my time, in units of seconds, the same units as what the rate constant have, okay? So it looks like to me, they're telling me that I'm going to wait 200 seconds, and I want to know what the concentration is after that 200 second period. So I'm going to multiply that 200 times my k, my rate constant. And that's all going to be equal to the natural log of my reactant at time t. Okay? So it looks like I'm off to a pretty good start here because I only have one unknown variable. If I do the math over here, if I do the multiplication and I add the natural log of this, it looks like I end up getting negative 1.93 for the right side of this equation, equaling the natural log of A at time t, and here t is 200 seconds, so I'll just make note of that, right? And now I'm going to take the inverse log, or inverse natural log, to find A 200, which is my concentration of A at 200 seconds. And if I do that, I find my concentration after 200 seconds is 0.146 molar. So it started out 0.15, I wait a couple minutes, 200 seconds, and the concentration drops to this.